Hi, welcome to lecture number 5. This is going to be a review lecture for midterm number 1, the material being algebra pre-calc, and just the beginning of limits. So where we talked about understanding what a limit is and also computing it when the answer is a number, not plus or minus infinity. So yeah, the plan for this lecture is just to give you a couple of problems and a little bit of review of the theory that applies to each problem. This is by any means not everything that you need to know for the exam. There's just too many topics to cover in algebra and pre-calc especially. But I selected a few of the ones that are very important, the ones that give people a lot of trouble as well. So I'll be solving problems. My suggestion is, as usual, that you should pause the video and try to solve them yourself first. And here is the first one. I'm giving you an equation that looks complicated and asking you to solve it. All right, so the solution for this, we have to realize that it's an equation that where a multiplication of a bunch of terms is equal to 0. And that can only happen if at least one of them is a 0. That's why I'm using the word or, by the way. We have the three terms being multiplied here, the exponential, the ln, and also this quadratic with a sign. We don't need that all three of them need to be 0, but rather at least one of them. So or is the word that we use. Now, when you look at the first one, you immediately realize that it's not possible. Each of the anything is always positive. Each of the x is positive for all x. So it can never be a 0. So that's already out of question. But the other ones can possibly be 0. In particular, let's look at the first one, ln. ln can be anything. There are positive, 0, and negative values for ln. You may be confusing. If you're confused about this, the thing inside of ln must always be positive, but the result might also be negative or 0 in this case. In particular, when is ln equal to 0? So let's solve this part. What is the number whose ln is 0? You can find that by taking e raised to the both sides of the equation. That will give you that the number inside of ln must be 1, which is e to the 0. So in other words, this is because ln of 1 is 0. 1 is the number whose ln is 0. Now we have to solve this. X plus 4 in absolute value equals 1. Remember that the absolute value of a number is the operation that just makes it positive. You can think of it that way. So in order for x plus 4 to be 1, you will need that x plus 4 is either 1 or minus 1. Again, the word or. Obviously, it cannot be both at the same time. It just has to be one of these options. And then its absolute value will be plus 1. And now you can solve each one separately. The first one gives you a minus 3. The second one will give you a minus 5. So we found the solutions making this second part, the ln part, equal to 0. Now I'm going to be solving the one with the sign. Let's say down here. Looking at this equation, sine square of x minus 3 sine of x plus 2 equals 0. It's not like you can isolate the sign. You have a square and also just a sine term. This is just a quadratic equation, but in disguise because the variable in this quadratic is the sign. So for example, if you call that some other variable, let u be sine of x, then the equation for u, you immediately recognize this as a quadratic equation. U minus e squared minus 3u plus 2 equals 0. And if you factor this, u minus 1 times u minus 2 gives you precisely this quadratic. Try to factor this any way you like. You can use the quadratic formula also. Solving a quadratic should not be a thing that you're having trouble with. This gives you the values u equals 1 or u equals 2. But those are only u, where we're trying to find it was actually x, where u is sine of x. So now we have, again, we need to study these two possible situations here. We're looking for numbers whose sign is 1 or 2. Well, sine of anything is always between -1 and 1. So this part we can immediately discard. Sine of x is always in the closed interval between -1 and 1. There isn't, you can never find a number whose sign is 2. But this part, sine of x equals 1, there are numbers with a sign of 1. And they are, thinking about the unit circle. That's a terrible circle. Let me do this again. Here you go. Remember that the measure of sine of an angle is found by looking at the y-axis. And here is the value of 1. So the angles with a sine of 1, well, the only angle between 0 and 2 pi is this one, pi over 2. But you should remember that sine starts repeating its values after every multiple of 2 pi. So this means that any angle that's pi over 2 plus an integer multiple of 2 pi is an angle that has a sine of 1. So you can write this as pi over 2 plus 2 pi n, where n is integer. That solves this part, the sine equation. Those are the solutions for that. Let me remind you that we had also these two solutions, -3 and -5 for the ln part, and we had no solutions for this exponential part. So you finally have your solution to the equation. It was -3 or -5 or all these angles here with pi over 2 plus 2 pi n, where n is integer. Now I'm going to be moving on to the next example. And before the example, I'm giving you some reminder here. This will be the general rule for today. Just reminder, it's just the definition of what the domain of a function is. The domain of a function is the set of the numbers x for which you can calculate f of x, for which this is defined. And in most cases, when the function is defined just by an expression and nothing else is said, like in here, in this example, I'm just giving you a formula for the function, then the domain is just all the x's for which the expression is well defined. So everything that does not cause problems with the expression. Now, if you look at this problem, it's kind of a long problem. You're not likely to find this on the exam, but I'm putting it like here in this example because it covers a lot of things that might show up in this exam or in future assignments. So I'm giving you a function that has many potential problems, and we want to find its domain. And also write it in interval notation. So for the domain, for this expression f of x to be well defined, we have three potential problems here. First of all, we need the thing inside of the square root to be positive or 0. You cannot take a square root of a negative number. And this time, this is an and. We need all of these conditions together, because if one of them fails, then the expression is not defined. So what is the next condition? For the ln, remember the thing inside of the ln must be strictly positive. It cannot be 0 either. You cannot take ln of 0. So and then finally, the thing that we have as a denominator, well, denominators cannot be 0. We need all these three conditions together. Let me call them 1, 2, and 3 because we're going to analyze them separately now. All three conditions will give us only specific values of x, and that's how we find the domain. So let's study number 1. When is this larger than or equal to 0? This is the topic of solving a quadratic inequality. But this one is an easy one because it doesn't have an x term. So we can basically just do moving the 2x to the other side and dividing by 2. Now you have to think, you can write this. I prefer to think of it this way. I always prefer to have the x on one side. So I'm basically flipping the inequality. X squared less than or equal to 9. What are the numbers whose square is less than or equal to 9? If you write that x has to be less than or equal to 3, that's wrong. It's like taking a square root on both sides. That's not how you solve an inequality with squares. Rather, x squared being less than 9, remember that negative numbers also have positive squares. So for example, the numbers between 0 and minus 3 will also be numbers with a square less than or equal to 9. So actually looking at the real line, all the numbers between minus 3 and 3 will satisfy this. So x belongs to this closed interval from minus 3 to 3. That is item number 1. 2, let me scroll back up, is also very easy. Absolute value of x minus 1 has to be larger than 0. How do we solve this? I'm going to move the minus 1 to the right side. Absolute value of x has to be larger than 1. That's also very easy if you remember what the absolute value means. Absolute value of a number means its distance from 0. So we're just looking for the numbers whose distance from 0 is at least 1. Or it has to be strictly larger than 1, rather. So that actually gives you these guys. Larger than 1 or also smaller than minus 1. For example, minus 2 would have an absolute value of 2, which is larger than 1. And in interval notation, this one, you could write that it's between minus infinity and minus 1, union 1 to infinity. You want to take those two intervals together. So in other words, you're saying x could be on the first one or the second one. That's why we use the union symbol. That's how you solve the second part. Third part will be easy. Here is the expression that we need to be different from 0. X squared plus 3x minus 10. When is that different from 0? This is just a quadratic inequality in this case. You can basically find the places where it is 0 and then you're looking for everything else. Well, if you factor this, let's see, two numbers with a sum of 3 and product of minus 10, that would be minus 2 and 5. Well, if you wanted to find the places where they are equal to 0, it would be 2 and minus 5. Because we're trying to make sure this is not 0, then you have to take basically anything else. Anything that's not 2 or minus 5 will, so you need those two conditions. You need both x different from 2 and from minus 5, then this will be different from 0. Once again, thinking about the line, you have 5 here and you have 2 here. And you want basically anything except the two numbers. So this would be from minus infinity to minus 5. Together, union with from minus 5 to 2, and then also with 2 to infinity. So we found the three conditions. But we actually remember that we wanted all three together, 1 and 2 and 3. So my suggestion here is to try to draw them all together. Let's see again, there was 0, there was minus 5, 3, 1. Remember now, the first condition was x is between minus 3 and 3, closed. The second condition was outside of this open interval from -1 to 1. So I guess it was like this. Open at -1 and 1. That was the second condition. And the third condition was everything that is not -5 or 2. No -5 and no 2, but everything else. Now we want to put all three together. You want all three to be satisfied. And so basically look at the places where all three are happening. You see that it looks like this. You can have -3. You cannot have -1. And then you start again at 1, but you cannot have 2. And that's about it. You cannot have the number 2 or 1 or -1. You can have 3 or -3. This is the only place where all three are satisfied. So in interval notation, domain was from -3 to -1. Sorry, closed at -3. Together with from 1 to 2, together with 2 to 3. It's 3 intervals, as you can see from the drawing. So as I said, this is kind of complicated for an exam question, but exam questions might have these parts separately. Moving on. Composition of functions. Here's a reminder of what that means. Given two functions f and g, the composite f circle g is this function where you first apply g. Notice that g is inside, and then you apply f. And this can only be defined when the range of g is contained in the domain of f. So in other words, the numbers g of x are numbers to which you can then apply f, which is not always the case. You cannot always compose two functions. But the problem that I'm giving here, please take your time to copy down these graphs. They look kind of complicated, but we'll see. The problem is showing you graphs of two functions f and g in green. Find the value of both f circ g and g circ f at the specific points 0, 1, 2, and 3. So I'm asking for 8 different things. Okay, so let's solve this. F circ g of 0, and then we want to do this for 1, 2, and 3 as well, and also g circ f. So what is that? F of g of 0. All right, so look at the graph. How do we find g of 0? 0 is this point on the x-axis. G of it is above that right here. This filled in circle here at the number 4 indicates g of 0 is 4. And what is f of 4? Let's look at the graph of f. 4 on the x-axis is here. And notice that there is an open circle up here indicating that is not the value of the function f. The closed circle is down here at the y value of -2. That's the value of f of 4. So we're going to be doing this for all these numbers. F of g of 1. What is g of 1? Looking at the graph of g, 1 would be around here. It corresponds to this section of the graph where g is horizontal. So all these numbers between 0 and 2 have a g value of 4. And f of 4, as we already discussed, is -2. Next is the number 2. F of g of 2. What is g of 2 now? Be careful, because when you're computing g of 2, this is an open circle, so g of 2 is not 4. The closed circle is down here. G of 2 is -2. And f of -2, let's look at the graph of f. Here's -2. Look at the closed circle. It's at the height of 4. So this is a 4. Last one, they were asking for the value at 3. It should be simple, f of g of 3. What is g of 3? The point on the graph corresponding to next value of 3 is right here on the x-axis. That if you look then at the y, like take a horizontal line, but from this point towards the y-axis, it goes right here at y equals 0. So it's a value of 0. And what is f of 0? On the graph of f, above x equals 0, you have this filled in circle here. F of 0 is 1. Now we need to do all this again, but with g circ f. 0, 1, 2, 3. Sorry, just copying this down very quickly. When computing this now, the innermost thing is the f. We're going to be looking at f first and then g. So f of 0 for the first one here. F of 0. That's something that we already had determined. It's right here. It's 1. And then g of 1. We also had discussed this already. G of 1 is 4. Next one here, f of 1. This will be interesting. We don't actually have the value for f of 1. If 1 is around here, all we know from this graph is that f of 1 is some number between 1 and 2. That's what I'm going to write down here because we don't have this information. Something between 1 and 2, strictly between. But then when you look at the graph of g, you see that g of something between 1 and 2 is again just corresponding to this place where the graph of g is horizontal. All these numbers have g equal 4. So even though we did not really know the value of the function f there, we can still determine g of that. Kind of a trick question here. Next one, f of 2. Basically the same thing will happen. What is f of 2? We don't know, but it's between 1 and 2. And what is g of anything between 1 and 2? It's 4. So we can write that this is g of, same thing here. Something between 1 and 2, and that's a 4. And finally, last one, f of 3. F of 3 is given as a 0. And then g of 0 is 4. So this example is showing us not only compositive functions, but also how to get values of functions looking at their graphs, specifically also the open circles versus closed circles when you want to indicate exactly where the value is. Here's the next topic, difference quotients. We briefly discussed this. If you have a function f, the difference quotient for a function is this particular expression here. It depends on two variables, x and h. What it represents geometrically, we've seen that, imagine that you have a point x and you have a point x plus h. Usually h will be a very small number. And you have the graph of the function somewhere. Basically, what you're looking at is the line on the graph. It's called the secant line. The line that crosses those 2 points on the graph, the point above x and the point above x plus h. That line, if you try to compute its slope by looking at delta y over delta x, it will give you this expression. Geometrically, this is what it represents. But for us, later, this will appear when we talk about the derivative. So that's why we usually like to give lots of problems involving this. And in particular, here is a problem where not only we're computing the difference quotient, but we're computing a limit of it. Let's read this problem. Consider the function x times root x. Compute the limit as h goes to 0 of this difference quotient in terms of x. And also they're telling us assuming that x is a fixed positive number. So pay attention to here that h is going to be the limit variable, the one for which you're going to try to plug in values. And x is just to be considered as a positive number. So the first thing that we have to do, also try to do this yourself, pause the video. But the first thing we have to do is replace the function with its expression, x root x. So in particular, f of x plus h, I'm going to plug in x plus h for x. So this is f of x plus h, and then minus f of x, the whole thing divided by h. We're trying to find this limit. Well, this is a case where the limit is not something for which you can just plug in h equals 0, because there is this denominator of h here. It would be giving you something divided by 0, so we have to do something more. We have to simplify this first. I encourage you to try to simplify this, and I'm going to tell you what a possible approach is. There are some approaches. The first thing that I would do here is actually distribute this square root with the two numbers x and h. Let me do that. So you have x times the square root plus h times the square root minus x root x over h. Why am I doing this? Because of the second term here. After we split these fractions, we're going to be able to cancel this h, at least from this term. And now the other two terms that are left, they both have an x, which we can factor. So that's the idea here. See if you agree. So the first and the third term, I'm going to keep them up here divided by h. And then the second term is the one that I'm splitting from the fraction, also divided by h. And after doing that, we can cancel this h's, at least in this other fraction, the second fraction. What is going to be left? Well, now x in this first fraction, I'm gonna be taking the limit of the first plus the limit of the second. X in the first limit is just a number. Remember that the limit variable is h. X can be brought outside of the limit. So you have this, and the second limit, the h's went away, becomes just that. I hope you see what I'm doing. Now you have to deal with the two limits separately. The second one is very easy. In the second one, you basically already got rid of the problem. You got to cancel an h, and now it's possible to plug in h equals 0. So this one will just be equal to root x. When you plug in h equals 0, it gives you root of x plus 0, which is root x. The first one still is not quite like that. We're dividing by h. We have to do something about it, and it's the case where you have a difference of square roots. So the technique that you should be thinking about here is the rationalization, or multiplying by the conjugate, which is what I'm going to be doing. So remember, there's an x outside, multiplying the limit. Let's keep it there. So I'm going to take this whole limit and multiply it, and also divide by root of x plus h plus root of x. And now the second limit was just root x. Let's write it down here. All right, now why do we do that? Because this simplifies the numerator. You have here root minus root times root plus root. This is simply going to become square of the first root, which is x plus h, minus square of the second root, which is x. Meanwhile, downstairs, you just copy down what the multiplication is. And now you can see what the point was, because you have x minus x, they go away. There is just going to be an h at the top, which cancels with the h downstairs. And suddenly you have gotten rid of the problem of the limit. Now you can plug in. It is possible to plug in h equals 0. Remember that the question told us x is a positive number, so that's why I know there will be no problems with h equals 0 in this expression. What does it give you? Something like this that you can now simplify. You have x divided by 2 root x plus root x. This is an acceptable answer, but there is a simplification that we can do here by rationalizing the first term. If you multiply and divide it by root x to get rid of the square root in the denominator, like this. So now root x times root x will give you an x in the denominator, which you can see is going to cancel with the x upstairs. That means you have root x over 2 plus root x. And I'm just going to keep going to simplify this as much as possible, factoring a root x. You have 1/2 plus 1, which is 3/2. So that is your final answer. 3 root x over 2. If you already know the derivative, by the way, if you've studied calculus before, you know that what we are computing with this limit of the difference quotient is the derivative of the function. So try to compute the derivative of this function and see that we got the right answer. All right, so yeah, this was again, complicated limit just to showcase different techniques that might happen. Now we're going to be moving on. All right, this is a reminder for us about the fundamental limits involving trig functions. I wrote them in a little bit more detail here. The following limits are true. Sine of x over x as x goes to 0 is 1. And in particular, if you flip that limit, if you write x over sine x, then it becomes 1 over 1, which is also 1. So I just wrote the two of them together here. We should always remember that. Meanwhile, cosine x minus 1 over x as x goes to 0 gives you 0, which is the other fundamental limit involving trig functions. And we have also discussed that in particular, if you multiply the x by some number, non-zero number like 2x, 3x, then the same things are true. So this is simply the change of variable in the limit. If x is going to 0, then this variable ax is also going to 0. So if you call that your new variable in the limit, you transform these guys into the previous ones, and the same values of the limit are to be found. So this is our reminder, and now the problem is specifically asking us to use that to compute this limit. I've done a similar limit in a previous lecture or recitation, I don't remember, where we basically multiplied by cosine x plus 1 and also divided by that to see what happens. It's possible to solve it this way. However, now they're asking us to use those limits. And the problem is that as we look at this expression, we don't recognize them. I mean, cosine x minus 1 is there, but there is no division by x. So we have to introduce that in there somehow. And also the sine of 2x is there, but there is no 2x upstairs. What is the solution to this? You introduce them yourself, but you make sure to actually not change the expression. So like we would like to have a 2x above and also an x below. We can do that provided we also cancel that. So we have not changed the expression right here. But I'm going now to rearrange it. Essentially, the reason for introducing this x was that we would like to have it downstairs here with the cosine term. And the reason for introducing this 2x is that we would like to have it upstairs for the sine term. Finally, the reason for introducing the other guys was, well, because we cannot simply multiply by this term. That would be changing the function, so we changed it back. So we have to do something about those extra guys. And what we're going to do is simply cancel the x's. It's just a 1/2. You can cancel the x because x is not 0. Because you're going towards 0, that means you're close to 0, but you're not equal to 0. And now you're good. The 1/2 comes outside. Limit of the product is product of the limits as long as they both exist. That's important, but that's going to be the case here because we already know they exist. This first one is exactly the fundamental limit for cosine. And the second one is the one for sine, where you have a number inside, the 2, and you also have it flipped. But that's okay. This is equal to that limit, as I remarked. So the final answer here is 0. Moving on. I'm probably going to skip this one. I'm just going to leave this on the screen here, and you should try. So I'm reminding you about this rationalization trick again. Expressions involving sums or difference of terms where at least one of them is a square root can often be simplified by conjugating. We've done this today already. So I had just put 2 problems in here involving that. But I'll let everybody try to think of this by themselves. I just want to move on to the last one because I don't want to extend the video too much. So this last example is reminding us about one-sided limits and this important property that a limit exists if and only if both of the one-sided limits exist and they are equal to each other. So I'm giving you 2 limits to be analyzed involving the modulus or absolute value function. So let's look at the first one. T is going to 4, and we have this particular expression. Remember that the absolute value of an expression, like t minus 4, the absolute value is equal to the expression itself when the expression is larger than or equal to 0. And we probably want to think of t here. We want to solve for t in this inequality. So that's the same as t larger than or equal to 4. And it's going to be negative that, so minus t plus 4, otherwise. So when the expression inside is negative, meaning t less than 4. So really an absolute value is a piecewise function disguised. And why is this important for a limit? Because now you can see that the function that we have in the limit actually has different expressions depending on which side of 4 you are. Which means that if you want to study this limit, you have to study it by each side separately. You know that you don't always have to do that when you have a limit, in particular with an expression that is just one expression for all values of t, then you can just study the limit itself. But in cases like this, where the expression changes depending on the side, you have no choice. You have to analyze it separately from each side. So let's do that first from the left. Well, if t is to the left of 4, that means it's less than 4. So we are on the second case here. The absolute value is actually going to be equal to minus t plus 4. And now you recognize here in this fraction that the denominator and the numerator just differed by a factor of minus 1. So you can basically, for example, factor a minus 1 downstairs in order to write this is minus 1 times t minus 4, and you cancel the t minus 4s. So it becomes 1 over minus 1, which is minus 1. That's the left limit. The right limit will change because now you are on the right side of 4, which means the expression, the absolute value is for t larger than or equal to 4, gives you t minus 4. So you see that the fraction now just simplifies down to plus 1. T minus 4 and t minus 4 get canceled, and you have a plus 1. And you see now two one-sided limits which are different, which means that the limit itself does not exist. All right, now item B is the one is included in here just for as a trick question, kind of. You see that the function is the same, t minus 4 over modulus absolute value of t minus 4, but the point on the limit is the number 3. So you have to ask yourself, this absolute value function, when you're computing a limit around 3, so you're really only interested for values of t close to 3. And what is t minus 4 when t is close to 3? Think of the number line. You have a number t that's somewhere here in either side of t of 3. Well, if you subtract 4 from that, you're gonna get a negative number. So t minus 4 is negative in this limit, and then the absolute value of that is equal to 4 minus t, because t minus 4 is negative when t is close to 3. And actually that doesn't matter from which side you are approaching the number 3. Both of these that I drew up here will give you a negative number. So in fact, this absolute value has just one value when you are close to 3. That means you can actually evaluate this limit directly. It will be the same from either side, so you can just compute it directly. T minus 4 over 4 minus t. And as we discussed above, this is equal to minus 1 if you cancel this fraction. So now, because the actual limit is minus 1, then also the left and right are both minus 1. Let me write f of x here. So it was a trick question. The fact that the point where you're computing the limit is not really a point where this absolute value changes sign. So it has one specific sign around that point. Anyway, so those were all the examples for this class. Again, please try to do these two yourself. The difference between them, by the way, it's just the number that changes. 2 and 1, try to think how it changes when you try to solve this problem. And let me know during office hours if you have any questions.